Hello everybody, welcome back. In this video, I want to do a quick introduction to polars and just talk about taking the derivatives of polar functions. And then in the next video, we will talk about finding areas in polar graphs. The AP really only asks us to do two things with polars, and that's find sometimes they're derivatives, but also like it's all about areas in the plane, right? So they're really big on asking us find the area in this polar curve. Sometimes it's find the area between these two polar curves, like an enclosed area. But outside of that, AP really kind of leaves us alone on polars. Okay, so let's talk about polar coordinates first. Again, you definitely did this, at least that's what I want to tell myself, in I keep calling it L5. It's pre-calc now, right? But just in case you forgot, or just in case you didn't, pandemic, then let's do it. Okay, so instead of assigning an XY coordinate to a place, into a point in space, what we do in polars is we define two things. We define how far away it is from the origin. That's a straight line distance, right? We call that R. And then we talk about how much of a rotation that is from the x-axis, from the positive x-axis. It sounds a little strange, but I think about it as r theta first. There's two different ways to think about it, right? I think of it as creating the arm first and then the theta. So for example, if I gave you a point 2 pi over 4, okay? This is my distance from 0, distance from the origin, right? And this is the angle from the positive x-axis. So the way I think of it is this. I think of a little arm that comes out 2, and then I am going to rotate that arm through pi over 4, and there's my point right there. Right? It's 2 out, rotate pi over 4. Some people think of it in the opposite way. They think about, let me think about standing at the origin and I'm facing out the positive x-axis. They say turn pi over 4 degrees and then take 2 steps. It's going to get you to the same place either way, right? If I'm standing here and I turn my pi over 2 and then go 1, 2 steps, it's going to get me to the same place. I think of it as r and then theta because I like the idea of physically turning that arm, right? How long is my arm supposed to be? And then rotate it to where it's supposed to be, like the hands of a clock. Okay, but anytime you see a coordinate like that, this is a polar. All right, so look, this value here can be positive or negative, right? If they put a negative pi over 4 on that, then it would be down here. Because I'm coming out 2 and then going negative pi over 4. So that said, there's more than one way to name the same point, right? Like, if I wanted to come over here, I could say it's pi or negative pi. So I could bring you around this way, or I could bring you around this way. It's the same thing. All right, so couple fun facts, just in case this pops up for you. Little kind of the simplest of polars. In Cartesian, if we hold, like, for example, x constant and allow y to vary, that gives us a vertical line, right? If we hold y constant and allow x to vary, that gives us a vertical line. We can think about the same thing in polars, right? If I hold r at a constant value, so let's say my only condition for this, they give me r is equal to 6. Okay, well, if they give me r is equal to 6 and they don't give me any restriction on theta, think about what that means. I need an arm that comes out 6, but theta can be anything. That is a polar equation for a circle. So in Cartesian coordinates, this would be x squared plus y squared equals 36. In polar coordinates, it's r equals 6. Pretty simple. Right? Writing an equation for a circle in polars is really simple. You want an equation for circle radius 10? Here. You want an equation for a circle of radius pi? Here, I did it. Now again, these are all centered at the origin, but I could shift them if I wanted. We're not gonna. Okay, same thing if I I can also do the same thing, I should say, if I hold a degree constant, but I let r go, right? So let's go back to our friend pi over 4, right? If I say, you know what, theta has to be pi over 4, but I'm going to let r vary. So you can go as far away from the origin as you want, and you can even go positive r or negative r, right? As long as theta is pi over 4, look what you get. You get a straight line. So if you have an r equals, it's a circle. If you have a theta equals, it's a straight line. So when we write equations for lines, as long as they're going through the origin, that is, they're real simple. If I want the equation for the vertical axis, the y-axis, it's just theta equals pi over 2. On the x-axis, that's theta equals 0 or theta equals pi. Okay, again, that's not like a huge, they're not going to ask you that directly, but it may come in handy for you as you're doing some problems. Okay. All right, so important. Converting Cartesian and polars, converting back and forth between Cartesian and polars. So notice this graph here is kind of like a Cartesian plane with a polar superimposed on it, right? So at every point out here, I'm just going to name it right here. Okay. I could name this is 3 pi over 2, or pi over 4, sorry, in polars. But I could also write that same coordinate in Cartesians, right? It definitely has an x and a y value. And I could convert between the two. The way that I do that is by using trig, right? Look, here's my arm, here's my r, here's the x, here's the y. It's just a little bit of right triangle trig. Okay. If you want to get your x value, if you want to get this, it's just pi cosine theta. I'm sorry, r cosine theta. So r cosine theta, because the cosine theta is going to be the adjacent side over the hypotenuse. Okay, if you want the the y, you want this distance, that's going to be r sine theta. So if I want these x and y values, all I have to do is say, okay, well, my r is 3, so cosine pi over 4, and y is 3 sine pi over 4. So they're both 3 root 2 over 2, right? Now look, looks pretty good. We knew these weren't going to be cute coordinates, and they're not. So you can always go back and forth between polar and Cartesian in that way. Now, we had talked about this idea too of the equation for a circle in Cartesians. There it is, x squared plus y squared equals r squared. This is like the big link between polar and Cartesian. And then we also know that in any triangle, just like we had over here, if I come out here, here's my x coordinate, here's my y coordinate of that point, right? Here's theta. The tangent of this theta is going to be y over x. Again, if you're in physics, these look very familiar to you, right? Because you are constantly taking r, or a vector, off at an angle, right? You're constantly saying things like, oh, the velocity was 57 meters per second at 30 degrees. Then you find the x component of that velocity and the y component of that velocity. You're taking a polar and turning it into Cartesian. Okay, so you have to know these formulas. Again, it's an equation for a circle and it's right angle trig. They're not new formulas, but you need to keep these in your pocket, because what we see is questions that give you a polar and ask you to rewrite it in Cartesian, or vice versa. They give you Cartesian and ask you to bring it back to polar, and we'll do a couple examples of that. All right. Okay, here's a polar, and they want us to rewrite it in, oh, I'm sorry, it's Cartesian. They want us to rewrite it as polar. Okay, that is the equation for a circle, but it's not centered at the origin. It's shifted. It's shifted up 3. I don't care. I'm going to turn it into a polar equation. Right? So there's only a few things that I know, but one of them is that x squared plus y squared is equal to r squared. Right? So if I can get an x squared plus y squared in here, I can replace it with an r squared. So let's do a little bit of algebra. So this is y squared minus 6y plus 9, right, is equal to 9. So look, this x squared plus y squared can get replaced with r squared. So now I have r squared minus 6y, and look at this, I'm going to subtract this 9 from both sides, equals 0. Okay, now look what else I can do. See this y right here? I've got to get it out. Right? If I want this to be polar, there can't be any x's or y left. Well, what do I know about y? Y is always going to be equal to r sine theta. So I'm going to rewrite this with that substitution. Okay, I can also write it as r squared equals 6r sine theta. Just move it to the other side, but there it is. I took my equation in terms of x and y, I turned it into an equation into r and theta, just using my facts that I know about right triangle trig. Okay, let's do another one. Here is polar, we're going to turn it back into Cartesian. Okay, so look, I could, if I wanted to, replace this r squared with an x squared plus y squared. I know that's true, but what am I going to do with this cosine theta and this sine theta? Right. So I know that x is equal to r cosine theta, so I could replace cosine with x over r, but that doesn't really help me because the r is still sitting there. Right. So a better idea here, since you have a sine and a cosine kicking around, is to separate that r out. So in other words, I can take one r and pair it with the cosine, one r and pair it with the sine. So this turns into r cosine theta times r sine theta. And that is a surefire way to get rid of your cosines and sines. This is nothing but an x. This is nothing but a y. So my Cartesian equation for this is just x times y equals 4. Or y equals 4 over x. So if you wanted to write it like that, you could. And we know what that graph looks like. So listen, sometimes it's helpful if you see this. We are much more comfortable with Cartesian coordinates, right? Everybody has an idea of what this graph looks like, right? This is the two swoops. I'll bet nobody had any idea what this graph looked like. But if you do a little bit of work to get it into Cartesian, sometimes it can help you figure out what the graph looks like. We are much, much, much more comfortable with Cartesians for obvious reasons. We almost never use polars. All right. Okay, so last thing I want to talk about in this particular video is the derivative of a polar. So it is exactly the same thing to take the derivative of a polar as it is to take the derivative of a parametric. The only difference is instead of time, your derivative is theta. So if I want dy dx, I need dy d theta over dx d theta. Okay. But you may have noticed the problem. The equation they gave us is r. I don't see an x or a y here. So I'm going to use this formula. But before I do, I have to find equations for x and y. And that's really not terrible, because I know that x is r cosine theta, and I know that y is r sine theta. So they gave me r. R is 1 minus cosine theta. So 1 minus cosine theta times cosine theta, and 1 minus cosine theta for y times sine theta. So all I have to do is take those derivatives. So I suppose we have an option here. We can either use a product rule, or we can multiply this out, so we have to use a chain rule. I'm a fan of the chain rule, so let's do it. So I'm going to rewrite this as cosine theta minus cosine squared theta. And down here, yeah, I guess it doesn't really matter. I still have to use a product rule, huh? Fine, I'll just use product rules. Okay, so if I want dy d theta, I need 1 minus cosine theta times the derivative of sine, which is cosine, plus sine times the derivative of 1 minus cosine theta, which is just sine, right? 0 minus derivative of cosine negative sine. Yes. Okay. So first derivative of second, second derivative of first. Okay. Got to do the same thing for x. And again, I will just use the product rule. So I had to anyway. All right. So this is going to be 1 minus cosine theta, the derivative of cosine, which is negative sine. I'm going to put the negative out here so it doesn't end up looking like minus sine. I don't want that. Plus cosine theta. Don't be lazy. Look what I did. I wrote t. Oh my gosh. I have to tell you something about that. All right, cosine theta and then derivative of 1 minus cosine, which is sine theta. So there's probably a little bit of simplifying that can be done here. Cosine, whoops. Distribute much? So this would be cosine theta minus cosine squared theta plus sine squared theta. And then this would be, let's see, negative sine theta plus cosine theta sine theta. Oh, you got two of those. Boop, boop. Okay. There's not a whole heck of a lot you can do here. Look, I need you to see something. This is so important. Resist the urge to go like this. This is 1. Because it's not. Because there's a negative right here, right? So this isn't cosine squared plus sine squared. This is negative cosine squared plus sine squared. In other words, it's sine squared minus cosine squared. Now, could you do stuff like that? Could you do trig identity stuff here? Absolutely. Should you? AP really doesn't expect you to do anything with trig identities other than sine squared plus cosine squared equals 1. And even then, it's like, if you want to. It's not really usually something you have to do on account of it's a calculus test, right? Not a test on trig identities. So this is pretty much going to be our answer because I cannot simplify that down very much. Okay. All right, so again, the derivative of a polar is probably the trickiest of the ones we're going to have to take because just like a parametric, you have to have the two components, right? But in order to get to this, you have to break it up using your right angle trig. All right, now, next video, last video, we're going to talk about taking the area inside of a polar curve. Any questions on polars so far? And